So I'd first like to thank the other organizers for the opportunity to speak here. It's a great pleasure for me to visit KIOS in a while. So I thought about it, and in fact, I think my last in-person visit was 4 years ago. So it feels so nice to be here again, and I'm looking forward to the exciting week ahead. Oops, I didn't want to. So today I'll be talking about a certain type of 7-branes stacks, which are typically discarded in the literature, despite the fact that they can actually be formed. Oops. So, and these 7-branes will be referred to as non-minimal 7-branes, or sometimes 7-branes beyond Kodaira for the reasons to come. And eventually, I'll show that they indicate decompactifications potentially with defects. So the talk will base mainly on these two drafts. I'm wrapping up with Timo Weigand and his student Rafael Alvarez Garcia at Hamburg. But before reporting on the recent progress there, I will first review some of the related previous analysis in these two works in collaboration also with Wolfgang Liehe. So let me start by clarifying what exactly we study and why we care. It is very well known by now that singularities in string geometry have interesting consequences for the effective physics. They often indicate extra massless degree freedom, and they also tend to come with symmetry enhancements. And arguably, one of the most prominent frameworks for such phenomena is F-theory, which is essentially the type 2B string theory compactified on a complex n-fold Bn with a bunch of 7-branes around. So for n equals 1, 2, 3, the EFTs live in D equals 8, 6, and 4 real dimensions, respectively. What's so nice about F-theory is that the dilaton profile sourced by these 7-branes is in one-to-one correspondence with the geometry of an elliptic fibration over this internal space Bn, which is of which total space is a Calabi-Yau n plus 1-fold Y in one complex dimension higher. And the main focus of this talk will be on 60 F-theory, described by the geometry of elliptic Y3 over B2. So back to singularities, the 7-brane gauge algebras are encoded in F-theory in the singular fibers over complex 4-dimension 1 loci on the base, Bn. And here, the allowed fiber types, or equivalently, the allowed gauge algebras, were classified a long time ago by Kodaira and Neron. They can be read off from the Weierstrass description of the geometry defined by the equation of this form. Here, x, y, and z are the homogeneous coordinates of the fibril ambient space in which the elliptic curve is embedded via this equation. And the coefficients, the blue coefficients f and g here, are sections of 4 and 6 times the anti-canonical bundle k bar of B2, thereby describing how these elliptic curves are fibered over B2 to form a Calabi-Yau Y3. Then delta, the discriminant, is defined like this as fq plus g squared, of which vanishing loci support singular fibers, thereby indicating that 7-branes lie there. So obviously, for this reason, brane moduli can be thought of as part of the complex structure moduli of Y3. Then in this setup, does it work? Yeah. The singular fibers are classified in terms of the vanishing orders of F, G, and delta. this table lists the so-called minimal Kodaira fibers, which actually sit at finite distance in the moduli space, resulting in a finite Lie-type gauge enhancement. However, obviously, this table should not stop here, because in principle, the vanishing orders of Fg delta could go beyond 4, 6, 12 at a time. And the associated badly singular fibers are known as non-minimal fibers beyond the minimal Kodaira types. Now, the non-minimal, any models with such non-minimal fibers are typically discarded in the literature just because mathematically such models lack a smooth Calabi-Yau resolution, rendering the physical interpretation rather obscure. However, F3 models with such non-minimal 7 branes do exist, and they call for a proper analysis to figure out the physics of those non-minimal 7 branes. Now, as I said, these minimal Kodaira fibers sit at finite distance in the moduli space, so you might think that these non-minimal ones would probably lie at infinite distance. And indeed, this turns out to be almost true. Modulo a small technical caveat, which I won't discuss today. But in any case, for this reason, non-minimal 7 branes, maybe I should just, non-minimal 7 branes are natural objects to study also in view of the so-called swampland program, in which a variety of conjectures are proposed and studied about universal features of all consistent effective theories of quantum gravity. So in order to put our story of non-minimal 7 branes also into this different context, let me briefly introduce 2 of these conjectures, which arguably sit at the heart of this intricate web of conjectures. One is the so-called distance conjecture, and the other is its refinement known as the emergence ring conjecture. And both of these conjectures concern the moduli spaces of quantum gravity theories. And for the purpose of this talk, these 2 conjectures we will view as concerning the moduli spaces of string compactifications. So they characterize universal asymptotic behaviors of the EFTs at infinite distance in the moduli space as we deform the compactification geometries towards the boundary. And the claim of the distance conjecture is that a tower of states should become light at infinite distance in this exponential fashion. And this interesting conjecture has been confirmed in various string setups. But this conjecture still remains as a conjecture. I say it's a conjecture. So to better understand this conjecture and develop further intuitions, it is then important to reveal the very physical nature of this light tower of states. And along this line, the emergence ring conjecture was proposed, according to which at infinite distance, the effective field theory either decompactifies or reduces to a weakly coupled critical string theory. And this is a refinement of the previous conjecture in the sense that the former case leads to a light tower of Kaluza-Klein states, and the latter to a light tower of string excitations. Strong evidence arises from many non-trivial string theory setups, both for the Kähler moduli and the complex structure moduli of compactification geometries. As for the Kähler moduli, the possibility of decompactification is perhaps looking like an obvious option. You can just decompactify geometrically. However, the emergence of unique critical light string is not as obvious and needs to be properly addressed. So the confirmed setups include F, M, and type 2 string theories on Calabi-Yau streetfalls, M theory on G2s, and eventually 4-dimensional F theory with only 4 real supercharges. As for the complex structure side, sometimes it's difficult to see how the space-time decompactifies. The initial evidence was from the closed string limits of type 2 string theory. And later on, we systematically analyzed the open string limits as well, realized as the complex structure moduli limits of F theory. So this provides an interesting perspective for our current story of non-minimal 7 branes in 60 F theory, because, as I addressed, those objects sit at infinite distance in the moduli space, in particular in the open string moduli space / complex structure moduli space of F theory. In fact, what we found about the 80 limits turns out to serve as an excellent guidance to the study of 60 limits as well. And therefore, I will first review our 80 results, the earlier ones, and building upon them, I will eventually analyze the 60 limits. But before we actually start our journey, let me actually add a few more relevant remarks about this emergent string conjecture. Firstly, the way this conjecture is realized in string theory is typically by invoking the string dualities. In particular, this conjecture asserts that every infinite distance limit in which the space-time dimension is kept fixed must be given a dual description in terms of a perturbative critical string. The established string dualities are, of course, examples of this phenomenon, but should the converse also hold? And this is one of our points. At least in many non-trivial string setups we studied, by carefully classifying and analyzing all infinite distance limits of string compactification geometries, we have been able to verify that this conjecture does hold. And in fact, its validity follows from a number of universal geometric properties that emerge at infinite distance in the moduli space somehow. And it just turns out that they work together so nicely to realize this conjecture in string theory. So at least to my surprise. And this way, we obtain interesting intuitions and lessons both about physics and geometry. There's also an interesting work aiming to undertake a taxonomic study of infinite distance limits, initially for 9-dimensional n=1 string theories. And in here as well, the string dualities turn out to play a prominent role in realizing various conjectures, including the distance and the emergent string conjectures. The other point I'd like to make is concerning some potential caveats of this conjecture. Firstly, as for the string limits, one could ask if multiple species of Lie strings could arise at all in a given limit. As it turns out, however, at least for all classes of asymptotic geometries we've considered and analyzed, we've been able to prove, either prove that the Lie string should be unique, or otherwise spot a KK tower which is lighter than even the lightest string scale. Furthermore, one could as well ask if higher dimensional objects could possibly be lighter than the lightest string. But circumstantial evidence has been found for quantum obstructions of such potential membrane limits. So we are still good. As for the nature of the decompactification limits, one might naturally ask if the Lorentz invariance of the effective field theory we start with persists after the decompactification limit is taken. As it turns out, defects may as well arise in the Branes limit, which is going to be one of our main results to be discussed in this talk. So after this rather long introduction, here is the outline of the talk. Having motivated our study of non-minimal 7 branes beyond the Kodaira types, in the next slide, I will give a one-page summary to clarify the scope and the main results of our analysis. And then after that, I will elaborate on the details in 2 parts. So in the first part on ATF theory, I will start by giving some rudiments of K3 degenerations in terms of the so-called Kulikov models in algebraic geometry. And then I will describe our geometric strategies to deal with non-minimal 7 branes, and I will interpret the results in geometry as a space-time decompactification. And then in the second part on 60F theory, by making analogy with the 80 counterparts, we will find that a variety of features we found in 80F theory are actually shared by the 60F theory setup as well. However, at the same time, we will find that a few novelties arise in 6-dimensional setup, which I'll discuss. And most notably, we will find that 60 defects could possibly arise even after decompactification. And then I will conclude. So indeed, let's start with a one-page summary of the scope and the main results. So a little bit more detailed fashion, let me describe what we do and what we learn. So based on the Weierstrass description of the F3 vacua, we analyze non-minimal 7 branes. Their general properties can be seen already from the 8-dimensional F3 setup. The allowed base of elliptic K3 surfaces is P1, on which non-minimal 7 branes will sit at a point with vanishing orders of Fg delta equal to or beyond 4, 6, 12. Then, upon performing certain blow-up procedures, we will find that the space-time should decompactify to either 10 dimensions or 9 dimensions by observing a light tower of KK states and an affine gauge enhancement. And some strong evidence will also arise from the heterodic dual picture. Next, some novel properties of these non-minimal branes will be studied through 6-dimensional F3 setup, for which the base will be either P2 or the Hertzsprung surface Fn or their blowups. But because we are interested in studying infinite distance limits here, at this stage, we will just focus on the vanilla Hertzsprung surface Fn, which is a P1 fibration over P1, because all the other bases will be just finite blobs away from this base. Non-minimal 7 branes will now sit at a curve on this Hertzsprung surface Fn, and our first result will concern classification of the eligible curves on Fn that can support non-minimal 7 branes. And they can be either a section or a fiber of this rational fibration. And in case they turn out to be a mixture of these two classes, then they turn out to be under many constraints, which I will clarify. And unlike in 8 dimensions, in 6D, the non-minimal 7 brane locus can in general and will in general intersect with the locus of minimal 7 brane, and therefore in relation with the interaction between these two 7 branes, we will have to carefully analyze also the physics of the minimal 7 branes. And therefore, we will classify also the minimal 7 brane types. And then, in the end, we will get to propose that the space-time in the limit should decompactify now to either 8 dimensions or 7 dimensions, possibly with 6-dimensional defect present. So let me now start elaborating on some of the details starting in 8 dimensions, unless there are questions so far about the basic setup and whatever I talked about. Okay. So an elliptic K3 surface has its Weierstrass model defined over the base P1, whose homogeneous coordinates I denote here by SNT. And the 7 branes here are located at the discriminant loci, which are just 24 zeros of these degree 24 polynomials in ST. And for this reason, we can deform the positions of the 7 branes by deforming the complex structure, and therefore the underlying mathematical framework to discuss the 7 brane configuration is the degeneration of K3 surfaces. And the degeneration of K3 surfaces we will describe by a threefold family of K3 surfaces XU. So at a generic value of u, we have a surface xu, which is a smooth K3. However, at the center, at u equals 0, we have the degenerate surface x0, which will degenerate into a union of component surfaces x upper i's. The degeneration of K3 is actually called a Kulikov model if it exhibits certain nice features, which I won't go through here. So these are some mathematical criterion for a degeneration to be called a Kulikov model. But let me just point out that these properties can be satisfied by going through certain operations which actually do not affect the physics. So via the base changes, which turns u to the some positive integer power, what we are doing is essentially to approach the central element more gently, nothing more than that. So we don't change the degeneration. We just change how we view this degeneration. So the physics is the same. And the blow-ups we will consider will in the end correspond to zooming in on the brane stacks. And that's just how we look at the branes, and that doesn't change the physics. So these two operations will not change the physics, and therefore, according to these mathematical theorems, we know that any limits of 8-dimensional F3 vacua should be given an equivalent Kulikov model description. So why do I mention this, and why do I want to find a Kulikov model? That's because Kulikov models are so nicely classified into 3 types. So type 1 is at finite distance, and the usual Lee type non-abelian gauge enhancement should belong to this type. But today we are interested in infinite distance limits, so we should be considering type 2 and type 3 Kulikov models. So let me tell you about what's known about the geometric configuration of the central elements of these 2 types of Kulikov models, very briefly. So the central element, as I said, will degenerate into a union of component surfaces x upper i's. And for the type 2 Kulikov models, we know that the component surfaces are arranged in this chain form. So it's just a linear chain form. Furthermore, the intersecting components should meet along an elliptic curve. And in our elliptic case, because we want this K3 to be the vacuum of F theory, we want this K3 to be elliptic. And therefore, in this case, each component should itself be elliptic over its own rational base in this form. And furthermore, we can say that there should arise 2 transcendental true tori that shrink in the limit, and we will denote them by gamma 1 and gamma 2. And then I will talk about the physical importance of these objects shortly. And then moving on to type 3, I don't have a picture here for type 3, but in any case, the component surfaces in this case will not necessarily form a chain shape as in type 2, but in any case, it's a bit more general form, and then the intersection of any intersecting pair of components will be a rational curve instead. And also, in this case, we will only find one shrinking 2 torus, which I'll denote by gamma 1. Okay, so this is how the degeneration will look at u equals 0. So let's say we are given some concrete F3 vacuum in 8 dimensions. Now, in practice, how can we actually turn it into a Kulikov form? There is a mathematical theorem that every F3 vacuum should have some Kulikov description, but how can we actually make it to be able to say any physics about this degeneration? So we have our geometric strategy developed here to elongate the degeneration via blow-ups at the non-minimal loci until the degeneration gets completely free of non-minimal fibers. So that's the strategy in words. So let me now describe this in pictures as well. So the central element here has smooth fibers generically. It's an elliptic K3. However, the starting point is the presence of non-minimal 7 brane. So at this specific blue point here, we have a non-minimal fiber, say at S equals 0. And therefore, the vanishing orders of Fg delta at this blue point will be 4, 6, 12 or higher than that. Now, thanks to these high vanishing orders, we are now allowed to blow up at this blue point. And by this, what we do is actually to, have a close look at this stack of non-minimal 7 branes, and we just resolve this into some, so to speak, component branes. So in the end, what we get is now this, it used to be single base P1, now turns into a chain of P1s, and this single stack of non-minimal branes now splits into multiple stacks of minimal branes in the end. So this turns out to be always possible by just blowing up along this point possibly multiple times. So once we get here, we could even try to get to a genuine Kulikov model by blowing up further, this time along the fiber as well. And this way, we can actually obtain the genuine Kulikov model. However, the F3 physics should already be clear at this Weierstrass level, so we don't actually have to do this. But in any case, what we learn from this is the following. So this is our observation. So depending on the vanishing order of delta, whether it's 12, precisely 12, or bigger than 12, the resulting Kulikov model, which is obtained via this procedure, will be of type 2 or type 3. So of course, as I said, they should sit at infinite distance, and indeed, we see that they are either type 2 or type 3. And this is how we observe. And note that I'm writing them as type 2A and type 3A, because there are also limits of type 2B and type 3B. These 4 subtypes of 2 Kulikov models at infinite distance were introduced in this paper by us, just because in this way, each different subtype will lead to a qualitatively distinct physics. However, today we are interested just in better understanding the physics of the non-minimal 7 branes per se, and for this purpose, we don't encounter subtype Bs. So we would just say type 2 and type 3 interchangeably with type 2 and type 3. Okay. Right. So let me now get into the physics of the end result of this procedure, which is the elongated degeneration. Without going through the details again, I'm not showing you how we actually get here, but let me just claim that we get here, and then let me interpret the physics of this end configuration. In the type 2 case, this is how the geometry will be at the end of this procedure. So we have a pair of rational elliptic surfaces, also known as DP9s. They are elliptic surfaces, and they have smooth fibers genetically. And these two surfaces intersect at their common elliptic fiber over this point P at the intersection of these two P1 bases. So now let's look at the these two base P1s a bit more realistically here. So in this picture, these P1s are drawn as spheres, and we have 12 red crosses each side, which are 12 branes on each side. And because we are looking at type 2 Kulikov model, we expect to see a pair of vanishing two tori as expected from the math theorem. And indeed, we can identify these two tori in this manner. So this I0 fiber, the smooth elliptic fiber at this intersection point P, we have two one cycles, SA and SB. They can now be fibered over this base 1 chain sigma, and they define two transcendental two tori, and they are vanishing because this base 1 chain can collapse, and therefore these two tori are very small. So then in M theory first, the M2 branes there can wrap on these two vanishing two tori, and therefore this way we can obtain a pair of light BPS towers, and these two light KK light towers indicate decompactification later. And also in F theory, these towers can be interpreted as 1, 0 and 0, 1 strings winding around this base 1 chain sigma. So again, we get a pair of light particle states, and both of these windings are allowed here by the trivial monodromy at this point P. So as I said, indeed, having observed a pair of KK-like towers, we propose that the corresponding physics should be decompactification to 10 dimensions by uplifting by 2. And this proposal is strongly supported by analyzing the dual heterotic frame, in which we can learn that the dual heterotic torus has the Kähler modulus diverging, and therefore we decompactify to 10 dimension, and this decompactification now manifests in this dual frame. And clearly, the asymptotic gauge algebra should be fully restored to 10-dimensional E8 times E8 because we go to 10-dimensional heterotic string theory. Okay, now about the type 3. In this situation, the central element, the degeneration, in the end, after this procedure I described, will turn into a chain of P1 bases and elliptic fibrations over them. But at least at the level of Weierstrass model, this is, again, the chain form as in the type 2 case. I told you that for type 3 models, the degeneration doesn't have to be of chain form, but at least once you blow down all the fibril things, you can get to the chain. And this is how we actually obtain. In any case, what we observe is this. In this case, now we have more than 2 components, unlike in the previous case. And on all the middle components, the genetic fibers, even the genetic fibers will be singular IN fibers. So the IN with N positive. However, at least one of the 2 end components will have to have generic I0 fibers. So at least we have at least one DP9 end component. Now let's draw this more realistic one once again. Looking at this one of the DP9 end together with this this other P1 that supports this singular IN fibers generically. So in this picture, as I said, this P1 supports a singular IN fibers generically, and in these fibers, the A cycle is collapsing. Now, such singular IN fibers, the generic ones, will also be shared by this P0 at this point of intersection P. So we also have IN fiber here. And because this is type 3 clinical model, by mathematical theorems, we should expect to obtain one shrinking 2 torus. And indeed, this can be identified easily by fibering these collapsing A cycles over this base 1 chain sigma. However, one big difference from the type 2 case I discussed earlier is that the B cycle now cannot be fibered over this sigma because of this non-trivial monodromy at this intersection point P. So only the A cycle can be fibered, and this way we can get only one vanishing 2 torus, which I'll denote by gamma 1. Now, in M theory, as before, M2 branes can wrap this vanishing 2 torus, and this way we will get a tower of BPS particles, which will be KK-like because you can wrap n times of this 2 torus. And in the F theory, this can be seen as 1,0 string, the fundamental string winding around this base 1 chain sigma. And this is allowed by the monodromy of IN at this point P, and the other string cannot wind around this sigma. So we can only get one tower of light KK-like states, and this way we propose that the corresponding physics should be space-time decompactification now from 80 to 9 dimensions. And again, strong support arises from the dual heterotic torus analysis. By using this known mirror map, at least available for E7 times E8 models, we compute the behaviors of the Kähler modulus and the complex structure modulus of this torus, and then realize that they both diverge now, but at the same parametric scale. And this strongly supports our proposal that it should decompactify partially only to 9 dimensions. Yeah, and also there is an alternative interpretation of this light tower of states in terms of an affine extension of the gauge algebra. So the local monodromy analysis dates back to 97 and 98, so it's a very old result. And more recently, the Saclay group actually has done the heterotic version of this analysis as well. But I actually really want to get to 6 dimensions, so probably it's better to skip over this slide here. to actually go down to 6 dimensions rather than going upwards. So let me actually now start discussing 6-dimensional F theory and non-linear branes in this setup. Okay, so discussions here will be very much analogous to our 8-dimensional discussions. And as I said, our base twofold will be Hertzsprung surface Fn, which is P1F fibered over P1B. And I will depict this base space typically as a square or a rectangle, and these base P1s and the fibril P1s will be denoted as the horizontal line in this square and the vertical line in this square, respectively. And the 7 branes now, which should live on the discriminant loci, are living on curves because it's just codimension 1 in the surface. So that's the difference from the 8-dimensional case. And once again, we can try to consider the moduli that correspond to the 7-brane configuration in the 6-dimensional setup, and that can be described in terms of, again, degeneration of now elliptic Calabi-Yau threefolds. So once again, we want to describe this degeneration in terms of now a 4-fold family of threefolds, XU. At non-zero U value, we have a smooth elliptic Calabi-Yau threefold, but at the center, at U equals 0, we have degenerate X0 as a union of component threefolds now. And one big difference from the K3 case is that now we are lacking mathematical classification results available for Calabi-Yau threefolds. It's just that the Calabi-Yau threefolds are much more complicated than the K3 surfaces that mathematicians do not give us useful mathematical classification results yet. However, because we are interested only in the fibril degeneration of elliptic Calabi-Yau threefolds for studying the brane moduli limits, we can just apply the Weierstrass strategy we developed for K3 surfaces even to the Calabi-Yau 3 cases. And indeed, we will this way try to obtain and read off the physics of these non-minimal 7 branes in the 6 setup. So that's what we will do. So as for a quick remark, side remark perhaps, for the 60 experts in the audience, I see many of them. So what we are discussing here is non-minimal fibers at codimension 1 loci on the base, exclusively in codimension 1. And if you translate this into a codimension 2 language, this corresponds to, well, this is at least associated with a certain codimension 2 singular fiber, but with vanishing orders bigger or equal to 8 and 12. It's very highly singular codimension 2 fibers. And this should be contrasted with the conformal meta story arising from the finite tensor transitions in 6 dimensions. So for this to happen, we need to still have a codimension 2 non-minimal singular fiber. However, this should be less than or equal to 812. So what we are discussing is an extreme version of this conformal meta in terms of codimension 2. But now we are describing everything in terms of the 7 brane loci, so we are using codimension 1 language here. Okay, so to again contrast with the K3 situation and 8D situation, back then we had 7 branes sitting on points of the P1 base of elliptic K3. However, now the 7 branes are lying on curves on this Hertzsprung surface, and therefore previously we had some structureless point where the 7 branes are sitting on, but now we have some inner structures of the curves that will be wrapped by the 7 brane, and therefore we need to better understand the curve structures that can be wrapped by non-minimal 7 brane stacks. And for this purpose, let me briefly tell you a few basics about the curves on the Hertzsprung surface Fn. So the cone of curves on Fn is generated by the section class H and the fiber class F. So it's a horizontal section and the vertical fiber. And these two are subject to these intersection properties. And now the curve classes will be called horizontal, vertical, and mixed if the curve is a section with either self-adjacent -1 or minus n or plus n, and it will be called vertical if it's a fibril curve, and it will be called mixed if it's a mixture of these two classes. So it's our nomenclature for curve classes, just natural one. And then now we get to constraints on non-minimal seven-brane loci. So I say that not every curve can support a non-minimal seven-brane, and that's because we have to impose pretty high vanishing orders along this curve in order for this to support a non-minimal seven-brane stack. And this leads to a concrete upper bound on the curve class, an eligible curve class for seven-brane locus. And that's because, for example, if you look at this biaxial section F, which lies in 4 times k bar, along C, we need to have vanishing order at least 4. So that means 4 times k bar should be bigger or equal to 4 times C. And that's how we get this upper bound on the eligible curve classes for non-minimal loci. In any case, we get this upper bound, and we also want the curves to be irreducible, because otherwise we should view this as multiple stacks of branes. So under these conditions, in the end, we are getting only this handful of curve classes that are eligible for non-minimal loci. So they are classified, and depending on the nature of these curves that can support, but that will support non-minimal loci, we say that corresponding model with such non-minimal stack, horizontal, vertical, and mixed at the level of model as well. So this is how we call the model with non-minimal seven branes. Yes, yes. Both, yeah, both component-wise, this should apply because this is a Morricone. This inequality is in terms of the Morricone. Yes, thanks. Okay, so this is how we classify the curve classes of the non-minimal seven branes. And then now we now start elongating the degeneration. Again, in comparison with the K3 case. Now, in the K3 case, what we had was, okay, so the central element had generically smooth fibers, and there was a non-minimal fiber, which is the non-minimal seven-brane stack. And we could blow up at this blue point to elongate this surface into a multiple component surfaces so that we don't have any non-minimal fibers anymore at the end of this procedure. Now, we do the similar thing. We can actually do exactly the similar thing for the Claudia 3. Now, the difference is that the non-minimal fiber is not on a point, but now they are sitting along a curve, codimension 1 locus. But we can still blow up along a curve at this central element, and then we end up getting an elongated version of the degenerate surface. And this way, we can also prove that in the end, we can get rid of all the non-minimal fibers, and we can get to a degeneration without, well, with only minimal fibers around. Oops. And then, yeah, just to make the drawing simpler, I just draw the central elements here, forgetting about the other smooth guys. And let's compare the situations better. Okay. In general, we may have to blow several times to completely get rid of the non-minimal fibers. So after one blow, we may still have slightly milder but still non-minimal brane. In each case, we have to blow up once again. We keep repeating, and then in the end, we can get to some degeneration without non-minimal seven brane stacks anymore. The same here, we can get here. So in general, we have to blow up capital P times, ending up with 1 plus P many components. But that's just something that we can just do. And also, one thing I want to say here is that now in the 6-dimensional case, which curve we lap with this non-minimal seven-brane stack matters. And for illustrational purpose, I will focus later on the case where this non-minimal brane wraps a horizontal curve. So that's how we'll focus. And because of this reason, I will also rotate these elongated versions by 90 degrees to make this intuitively clear that we are blowing up along this horizontal curve. Okay, and well, for visibility, once again, I will actually align all these components just vertically rather than giving angles, so that we can look at the physics more clearly. Right, and one thing I want to point out here is that in 6D, unlike in 8D, where we had all P1s for all these different components for the basis, now we have still Hertzsprung surfaces, but they can have different twisting. So the K here for the Hertzsprung surface of the newly inserted component can be different from N in principle, and this K is actually determined as the self-intersection of this non-minimal locus. But because we will be focusing on the okay, so but before saying that, let me actually also to compare also with the K3 situation. Now we say non-minimal here, but they can be now, at least in K3 case, divided into 2 and type 3, and we classify it the same way for the Calabi 3 with quote unquote for 2 and 3, and this way we still see that in the former type we have generic I0 fibers everywhere, as in the K3 case. In the latter type, we have, in the middle component at least, a generic singular IN fibers. But at least in this talk, we focus mainly on the 7-brane loci, so we won't really distinguish these two cases, but we can in principle describe all the specific geometries, even the generic fibers. And also, as I said, we will focus on the horizontal 7-brane locus, and this way we can say that K is now equal to N because it has self-intersection plus minus N. So now we look at the minimal 7-brane types. As I said, this non-minimal stack will in general intersect with the minimal stack, and therefore, in relation with their interaction, we should also analyze the minimal brane types. So again, in the K3 case, things are much simpler because the minimal stack will not touch or will not see the non-minimal stack, and therefore, after the blow-up as well, this will remain in the 0th component, not seeing the division of this non-minimal stack. However, firstly, even in 3-fold case, if the non-minimal brane was also horizontal, like the non-minimal one, then this will not hit the non-minimal locus, and therefore, this will be this will not be affected by the blow-up procedure. However, if we have minimal branes vertically, or if we have minimal branes in a mixed way, then this will also have to be stretched along the blow-up procedures, and then we get some complicated global configuration of these 7 branes. So in order to get some intuitions about possible global 7-brane configurations, let me show you a couple of models before I conclude. So here is model number 1. I don't read the equation for you here. Let me just describe what is to happen. So we just blow up along this horizontal non-minimal, say type 2A locus. And in the end, we get this 2-component configuration by blowing up here into 2 components. And here, after the elongation, the used to be horizontal minimal brane, again, remains as a horizontal brane on the 0th component. This doesn't see the effect of the blow up. And also this vertical brane over there will just simply stretch to the B1 component after the elongation. However, this other vertical brane, strangely, will turn into 2 irreducible loci at the global level after the elongation. So in case you wonder why and how such a used to be vertical brane could possibly also extend along the horizontal direction, in fact, these are two irreducible loci, and I was skipping, but the first locus is just purely vertical extension, and the other second locus is, well, vertical, at least on the 0th component, but horizontal on the first component. It just turns out as such in this example, and this is a bit confusing. However, what happens here is in the end that this vertical brane is actually a combination of this and part of this non-minimal horizontal stack, so that after the elongation, this can also stretch horizontally. But in any case, this is perhaps some details. The lesson we can draw from this example is that branes coincident in one component after the elongation may actually be distinct globally. So from this, we are suggested to perform some global analysis to be able to properly identify the brane content. And here is the other model I wanted to show you. Again, there is a model. We blow up along the non-minimal locus. We end up getting this two-component configuration. So the usual story, the horizontal minimal brane here remains horizontal on the 0th component after the elongation. And the far left vertical brane is still just simply vertically extended. And the same is true for the 3rd vertical brane, just a simple extension vertically. However, the remaining 2 vertical branes will now combine into one irreducible locus after the elongation at the global level. So again, you might wonder how this could happen because these are 2 separate vertical 7 branes. How could they actually be combined after the elongation or after actually zooming in on it? And secretly, what happens is that these 2 vertical branes that looked like they are separate, they are actually joined by part of this non-minimal stack so that they could actually combine, and they do actually combine upon elongation. So again, in any case, the lesson we can draw from here is that multiple irreducible curves in one base component may in fact belong to a single stack of branes at a global level. So this can also happen in 6 dimensions. So global analysis is required again. Okay, so this is the last slide. So we're sticking with this second example. Let's try to interpret the 60 physics limit as fibration of 80 limits. So geometrically, our base twofold is on Hertzsprung surface, which is P1F over P1B. So if we pick one point on this P1B of Fn, then we get a copy of P1 fiber, over which we can define an elliptic fibration, which will be a K3 surface, which itself will be a fiber within the Calabi-Yau threefold Y3. So this is a nested elliptic K3 fibration. And for the generic enough K3 fibers of this type, generically chosen fibers, once we take the limit, they will turn into a Kulikov model of type 2A if we start with a horizontal model of type 2A. And this way, we know that from 80, the genetic physics is leading to 2 light KK towers. And this indicates that 2 extra dimensions will open up. So we decompactify from 60 to 80. And we also have these 2 special fibers, special K3 fibers, which are filled by vertical brane completely. And this already indicates that the higher dimensional Lorentz invariance after the decompactification is done should be broken. So the vertical gauge modes on them do not combine with the KK modes. So we will end up having some 6-dimensional defects, which are these vertical branes. So here is our proposal for the physics of horizontal model of type 2A. So the physics proposed is, again, decompactification from 60 to 80, and 6-dimensional defects are associated with such vertical branes if they are present. And again, the asymptotic gauge algebra will be fully restored to 8-dimensional E8 times E8, as in the Kulikov case, where things were restored to 10-dimensional E8 times E8. However, the asymptotic gauge algebra in 80 should be also endowed with 6-dimensional gauge defects to do with these vertical branes, which we can also classify. So this brings us to the conclusions. So what have we done? So we have studied non-minimal 7 branes beyond Kodaira in F-theory. They are largely ignored in the F-theory literature because, as I said, there are no smooth Calabi-Yau descriptions for those configurations. But our proposal, in math terms at least, is that the physics should be manifest from the configuration that involve local Calabi-Yau spaces, which are essentially the newly inserted components in the degeneration that are elongated. In any case, such non-minimal 7 branes provide a rich variety of infinite distance limits now in the open string moduli space. And this challenges the emergent string conjecture because the conjecture had mostly been tested in the closed string sector of the moduli space. So what happens? We've seen that firstly in ATF theory, by analyzing the degeneration of elliptic K3s, firstly we could give a systematic strategy in geometry, and from that we could zoom in on the non-minimal brane stack to figure out the actual physics that's happening there, and this way shrinking two tori have been explicitly constructed, of which existence was known by math theorems already. And associated light KK towers indicate decompactification of the spacetime to 10D or 9D, and such decompactification was strongly evidenced also by the heterodic dual picture. And in 6DF theory, it was now through the degeneration of elliptic Calabi threefolds, despite the lack of mathematical classification results, by extending our K3 strategy, we could also successfully zoom in on the non-minimal stack on the Hertzsprung surface base. And this way, systematic analysis in 6DF theory has also begun. And the generically light KK towers indicate, again, decompactification now to 8D or 7D. And as some novelties in 6 dimensions, we've seen that various minimal 7-brane types can arise in relation with some rich intersection inner structures of the brane loci, and vertical 7-brane in particular leads to 6-dimensional defects upon decompactification. And then this nicely fits in with the emergent string conjecture because we claim decompactification. But you may wonder, well, the geometric strategy we've developed here is applicable also to pure QFT setup. So is it really quantum gravity effect or just a QFT effect? And my take would be it is actually quantum gravity effect, but with this speculation, I will close my talk. Thank you very much for your attention.